Hey everybody, so we are going to discuss unit circle construction today. So this is a finished unit circle, and this is what a lot of people see. Even if you did a Google search for unit circle, this thing would probably come up. But there's a lot of questions of like, okay, well, where do all these numbers come from, right? Like, why is this the way that it is? So we're going to go through today and we're going to actually recreate this and do a construction on it. And then maybe it would be easier once that's finished, um, to be able to recall the unit circle instead of just trying to memorize it. If you're able to construct it, it might be a little easier to recall. So let's get going. So let's get our build on. So first off, so here's we are with a blank unit circle. And there's a couple things that we first off want to put in. So up to this point, what we know is we know trig functions of special angles. And we also know radians. And we also know trig functions of those like special radians. Okay, so what are the special degrees that we know? Well, we know sine, cosine, and tangent of 30. We know sine, cosine, and tangent of 45. We know sine, cosine, tangent of 60. And what we're going to figure out is sine, cosine, tangent of 90. Excuse me, 90. There we go, as well as 0. So first off, these are the degrees that we're going to put down, and you can see that these degree slices are all similar, right? You guys can see the symmetry from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4, right? They're perfect, basically replicas of each other, which means every kind of what we'll call the large slice is 30 degrees. So look, 0 to 30, large slice. 30 to 60, if you ignore the 45, there's a large slice there. 60 to 90, large slice there. So every time you see a large slice, you know that's a jump of 30 degrees, right? So then this would be large slice, jump of 30 degrees. Large slice, jump of 30 degrees. Large slice, jump of 30 degrees. And you would just keep going all the way around. Large slice, jump of 30 degrees. Large slice, jump of 30, jump of 30, jump of 30, jump of 30. And then you're like, well, wait a minute, what about all these in-betweens? Well, notice what's the pattern here be with the in-betweens? The in-between, I went from 30 to 45 to 60, so all the teeny slices are 15. So add 15, add 15, add 15. Done. And now our degrees are all finished. So that's the first part. The second part is now before we drop in our radians, right? Because then we're just going to drop in what all of our equal radians are all throughout here. We need to know a couple facts about the unit circle. And one of them is that the equation for this unit circle comes as x squared plus y squared equals 1. Now, what does that mean? So if you've never seen equations of a circle before, that means this is a circle centered at 0, 0, so as we have here, and the radius is 1. So the radius is equal to 1. So if the radius is 1 all the way around, the whole radius, always 1. All the lengths of all these guys, all 1. 1, 1, 1, 1, 1, 1, all the way around. So therefore, what does that give us? Well, that gives us, let me do this in a different color, that gives us all of these coordinate points, right? If the length is 1, I went 1 in the x direction and 0 in the y direction, so that's going to be the point 1, comma 0. What about here? Well, I went 1 in the y direction and 0 in the x direction. Over here, negative 1 in the x direction, 0 in the y direction, and down here, 0 in the x direction, negative 1 in the y direction. Okay, so we start filling in some points because we knew that the radius was 1. So now the question is, well, how do I know all the points here? What are all these coordinate points? Because it's not an easy 1 or 0 like the rest of these. Well, we're going to use what we know about trig functions of special angles. And how are we going to do that? So let's just show one. So we do what we love to do, and we create right triangles. So here's theta here. I know that theta is equal to 30 degrees. So the question is then what is this point here? Well, how do I get to this point? I go so far in the x direction, and I go so far in the y direction, right? So this is the point x comma y. So what do I need to do? I need to figure out my base side, and I need to figure out my height side, and I'll have that. But interesting enough, what this is this is going to be the same. So if we solved all of this out, what would we find? We would find that the x coordinate, right? I take 30, I have, oh, sorry, and I also always know that this length is 1 in my unit circle. So how would I find my x coordinate? Well, according to theta, x is adjacent, and I know my hypotenuse. Who deals in adjacents and hypotenuses? Well, let's just throw it over here. So cosine of theta would be adjacent, which is x, over hypotenuse, which is 1. Oh, what's anything over 1? Itself. So cosine of theta is always the x coordinate. This is huge. The x coordinate everywhere on the unit circle is literally just whatever cosine of the angle is. Cosine of the angle is x on the unit circle. Similarly, what about sine? Well, sine of theta is equal to what? Opposite over hypotenuse. Opposite over hypotenuse. Hey, y over 1. So sine of theta is going to just be y. So every coordinate pair around the unit circle is just going to be cosine comma sine. That's it. So we can calculate each one of these because I know what cosine of 30 is, I know what cosine of 45 is, I know what cosine of 60 is, and I know what cosine of 90 is, right, all the way around. Also, we already have this coordinate pair here. So if I use what I know about trig functions of special angles, and it always goes cosine theta comma sine theta, right, for all x, y coordinates around. All right, well, this is going to be, what's cosine of 30? That's the root 2 over 2. What's sine of 30? That's 1/2. So I know that coordinate. Okay, what about 45? Oh, that's where they're both root 2 over 2. Okay, what about 60? Oh, that's now when cosine now is 1/2, and that's when sine is now the root 3 over 2. Boom. Quadrant 1, all done. Now, I don't need to figure out cosine and sine of all of these guys because I know that I have perfect symmetry, right? Which means these coordinates are going to be exactly reflected over here because it's a mirror. So because I have an exact reflection, so now I'm in quadrant 2. So in quadrant 2, right, what do I know about cosine? Well, I know cosine is negative, so I'm going to take the same cosine, and now it's negative. What do I know about sine in quadrant 2? Well, sine in quadrant 2 is positive. So I'm literally just going to repeat all these values all the way across my circle, just using what I know about my reflections. Okay, and now these guys are reflections. Okay, so again, what do I know about cosine in quadrant 2? It's negative. What do I know about sine in quadrant 2? It's positive. Okay, and let me sneak that in there. That wasn't very good for space, but so now I know that guy. Okay, these two are also reflections. So again, my cosine is the same. It's just a different sign. So now I have negative root 3 over 2, but sine is still positive. And then we just repeat this process all the way down, right? Now who's reflections of each other? Well, these guys are all reflections of each other, right? Well, these guys are reflections of each other. And now I'm in quadrant 3. Well, in quadrant 3, cosine is still negative. And sine is now also negative. So that's a reflection. These guys are reflections. So quadrant 3, everybody's negative in quadrant 3. So we're negative root 2 over 2, comma, also negative root 2 over 2. Again, put a terrible parenthesis in there. And then these guys are reflections. Okay, so everybody's negative again, so I'm going to take the same coordinates. So negative 1/2, comma, negative root 3 over 2. Okay, and we have these coordinates again. And then I can play the same game and reflect these guys over this line. So these guys are reflections. Also, we could take quadrant 1 and reflect it over to quadrant 4 as well. So these guys are reflections too. So now I'm in quadrant 4. So in quadrant 4, cosine is positive and sine is negative. So now cosine is positive, sine is negative. Okay, let's reflect over here. Cosine is now positive. Sine is now negative. Terrible parenthesis to complete that. And then these guys are reflections. So again, cosine is positive and sine is now negative. But notice all values just repeat all the way around. It's just, okay, now who's positive and who's negative? So really, if you just know how to construct quadrant 1, you get everybody else for free if you understand how all of these reflections work. And that is how the unit circle is built. And here's the finished product, much nicer and neater than what I had, but now you can really see everybody gets reflected all around. And then just throw in also, right, 30 is pi over 6, 45 pi over 4, 60 pi over 3. And then we just have our radian to degree conversions all the way around as well. And so notice every big slice is 30 degrees. Every big slice is also a pi over 6. So pi over 6, another big slice, pi over 6 plus pi over 6 is 2 pi over 6. What does that reduce to? Pi over 3. Go another big slice, then that would be 3 pi over 6. What does that reduce to? Pi over 2. Go another pi over 6, another pi over 6. We literally keep adding pi over 6, 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 blah, blah, blah. All right, think of pi over 6 as literally just adding 1 over 6, right? We can add fractions, just add 1 over 6, and that's the way that it works. And now these really, really big slices are all pi over 4s, or think of them as quarters. 1 quarter, 2 quarter, 3 quarter, 4 quarter, 5 quarters, 6 quarters, 7 quarters, 8 quarters, done. Okay? So I hope that helped illuminate a couple things about how the unit circle is constructed. I also hope it helped now maybe that you understand the construction when you have to use the unit circle. I hope the recall now is a little easier than just staring at a circle with a bunch of numbers and dots and coordinates and radians and everywhere, and you're like, how am I ever supposed to remember this? Construct it a couple times, and I guarantee you that you will never forget the unit circle again. Thanks for watching, you guys. I'll see you next time.